All right, this is Mr. Wyrick. Today I'm going to kind of go over this semester exam note card. I put some things on here. We have this angle of theta coming across from this angle. We have our opposite side coming across from the 90-degree angle. We have our hypotenuse, which means this is our adjacent side. Sine is going to be the opposite over the hypotenuse. Cosine is going to be the adjacent over the hypotenuse. And then tangent is going to be the opposite over the adjacent. Always, always, always. So you can remember SOHCAHTOA. But these are what those ratios are going to look like. You've probably answered some stuff on the Delta Math about this. A figure with rotational symmetry, I like to think of like an S. Because you can tell what's going on with an S. But there's no actual like line of symmetry that you can draw through it to where it would go up and down, left and right, anything like that, and fold in half. But if you rotate to where the bottom comes up to the top, it's going to be the same thing. You should be able to flip an S over and it's still an S. So that's that rotational symmetry that we're talking about. Reflectional symmetry, I like to think of like a square or a butterfly is a very common kind of thing where we can draw a line down through it and it's the same on both sides. A figure with both symmetries, I like to think of maybe an equilateral triangle where you can draw the lines through it, but you can also rotate this edge to the top and rotate this one around and you end up with the same shape. That one's going to have both. Translation of a point on the graph. You always have x comma y. And if you move it to the right, you are adding to the x. If you are moving to the left, you're subtracting from the x. If you move it up, you are adding to the y. If you move it down, you are subtracting from the y. Just make sure that you understand kind of what's going on there. Rotation of a point on the graph, here's what I would do. There's a whole formula about like you can take x, y, and apply the different things, but what I would do is just draw it and then go ahead and rotate your entire graph like that so that you can see what's going on. And then, recount that point. Reflection of a point over the x or y axis. Again, it's easiest to just think about it. If you reflect over the x axis, you're taking your point like this and you're reflecting across here, the x value stays the same, the y flips. If you have your point here and you reflect over the y-axis, you're coming back here, the y stays the same, the x flips. So you keep the axis, okay? Whatever axis you're flipping over, that's the value that you're gonna keep. Dilation of a figure by the scale factor, you always just multiply. Dilation is where you get bigger, you get smaller. If you get smaller, you're multiplying by like a fraction, so 1/2, 2/3, 1/8, something like that. If it's getting bigger, you're multiplying by a whole number, so like 3 or 4 or something like that. And you go ahead and multiply both the x and the y by both of those numbers. The methods for proving the triangle congruence, that is side, 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 angle, side, angle, side, angle, angle, side, and hypotenuse leg. All those very specific ways that they go together. The method's not proving the triangle congruence. If you have all three angles, that's only enough for similarity. If you have angle, side, side, I'll put that as side, side, angle, so I'm not writing anything terrible. But there's no donkeys in geometry. This one is not going to work. This one is only used for similarity, so you just kind of move from there. Triangle proportionality, here's the deal. BA is going to be proportional to BD because these are parallel, so this angle is going to be the same as this angle. And this angle here is going to be the same as this angle. So we have angle-angle similarity. So it's just like you can put the big one over the small one. And if you're asked to put something equal to that, it's another big one over a small one. If it's flipped to where you have small over big, you just flip the other one to where you have small over big. If you have a big one over a big one, you just make sure that it's the corresponding side. So if I say BA over AC, then that's going to correspond to BD over DE, those same sides, but on the smaller one. What proves a parallelogram to be a rectangle, a square, a rhombus? Rectangle has all right angles, and the diagonals always bisect, but the diagonals are going to be equal in a rectangle. If you have a rhombus, the sides are going to be equal, and those diagonals are going to be perpendicular. They're going to make those 90-degree angles. So for the square, it has to be both. It has to be both a rectangle and a rhombus. All the sides the same. The right angles there. Yeah, that's where we are. The equation of a circle with center HK and a radius of R, this is going to be x minus h squared plus y minus k squared is equal to r squared. So if you're supposed to find the center is hk. The radius is the square root of this number over here. You should be able to see what it looks like just from the equation. Inscribed angles and central angles. If I have a circle and it has a 90-degree central angle, then this arc is also 90 degrees. If I have an inscribed angle coming back from here, this angle is going to be 45 degrees because the arc is 90. So the inscribed angle is half the arc, or if you have an inscribed angle, the arc is double that. It just depends on which direction you're going, but the central angles in the arc are the exact same. Arc length. If you're supposed to find arc length, like specifically the length of the arc, like measure, it's going to be 2 pi r, because that is your formula for circumference, and then you multiply that by theta, which is your angle out of 360. So if I have a 90-degree angle, 90 out of 360 is 1/4. So I could find the circumference, and 1/4 of the circumference is going to be the length of that arc. Not the measure, but the length. Okay? Finding angles formed by chords inside a circle, finding angles formed by secants outside a circle, finding angles formed by secants and tangent. These are all related. If you have, if I could draw this, I really need both hands. If I have a circle and I have some chords crossing inside that circle, then I have arc A and arc B on the outside. It's going to be, I add them together and divide by 2. So I'm averaging those two arcs to find what those angles are going to be. The secants outside the circle, this is for anything that's outside the circle, whether it goes through or if it just touches. We have A out here, we have B here, and then we have our angle. The angle is A minus B divided by 2. It shouldn't be negative, so always take the big one, subtract the small one. And then the secants and tangents and all that kind of stuff. Basically, this one is a lot easier than it seems like it should be. If we have a secant here and we touch that tangent at the point of tangency, then this is just an inscribed angle. So if this is arc A, it's 1/2 of A. Okay, just an inscribed angle. Area of a trapezoid. If you have a trapezoid, we have A and B. We're going to take A and B and divide them by 2, and then we're going to multiply that by h, the height. The parallelogram, it should be just the base times the height, but it should be your true height at 90 degrees, not some kind of slant height. Volume of a pyramid, 1/3 the area of the base times the height, and then volume of a rectangular prism, that's big B, area of the base multiplied by the height. Hopefully this gets you everything you need. You can ask any specifics. Remember, you can use the back to kind of write stuff in, draw it, put in explanations, anything more that you need, and you can use this on your final exam. Good luck.